Okay, let's wait for a few minutes. We'll see if anyone will join and then we'll start this session. In this session, we will study again some basics, how to follow the questions, and we will have something related to the frequency response. Okay, uh, this is week 11. Start with the some basic questions. This is, I hope, will be easy for you guys as well. So let's try these. We have been given the circuit. The values of device parameters are given K, VTH, lambda is 0, so there is no channel modulation. The values of the components R1, R2, RD, RD, VDD is 1. We have to find small signal voltage mean. That means we need to draw an equivalent circuit Assume signal coupling capacitors, that is, this capacitor are shorted for the input signal. Select the correct. Okay, so basically C1 is shorted. Now small signal analysis. That is frequency of operation is such that C1 acts as a short. Okay. So, if I draw an equivalent circuit, so I make this as V input. This is R1 parallel R2. Okay. This is source. This is GM. And there is the combination, so I can directly write GM in. Ignoring the generic modulation, it is simply RD and it will be V out. So V out will be minus times GM RD V in. Therefore, the output by the input, that is your gain, is equivalent to GM. Now you have to calculate GM. What is GM? We know ID is K VGS minus VTH whole step, and GM is scale. Okay. So this will be K W by L VGS minus VTH. And now K is given, KW by L is given, that is 1 milli. What is VGS? VGS, we're talking about your DC voltage, that will be R2 divided by R1 plus R2 multiplied by VDD. Right? So VGS is R2 is 20K divided by 20K plus 60K multiplied by 12. K will go. VGS comes out to be 3 volt. Okay. And VTH is given as 1, so this will be 3 minus 1, so it will be 10 millisieverts. So GM is now calculated. We only need RD, that is given, so it will be 2 milli into RD. RD is 2 kilo ohm. So therefore, gain is 4. A very simple question. Should be easy for you guys to solve as well. And then next, so okay, again we need to find the input resistance of the circuit. So this was our circuit. So how we calculate input resistance? Here, right? Connect the test source, Vx, right? Simply you can see that Vx will be Rx times R1 plus R2. This implies this is Zin, right? Input impedance or input resistance will be Vx by Rx, and that will be equivalent to R2. So let's plus 4. So that is actually 20K multiplied by 60K divided by 20K plus 60K. Okay, Q1, here we go. So this will be 20 multiplied by 60 divided by 50. Okay, so this is equivalent to 15K, right? Okay, 15K. Okay, now similarly we have to calculate output resistance. Let me just draw the output one. This is 0 in. Since V in we will connect to 0, so this will be 0, and this here will be RD, and I will connect here Vx, this will be Ix, so Vx will be Ix times RD. Simple, so R out will be Vx by Ix, and X simply will be equivalent to RD, and that is given to us as 2 kilo, right? I hope this is very clear. I have done a lot of these kind of questions. Okay, so this is part E part, and that is E option E. Okay, long is the answer. Okay, now if there is um, confusion, so we can move on to this part. This part says we have to calculate a value of capacitor C1 such that lower cutoff frequency of the amplifier term is 10 Hz. Okay, so there are frequencies, three kinds of frequencies in the circuit analysis. One would be lower cutoff, mid frequency range, and upper cutoff. Okay, so this is mostly governed by input capacitors, and these two, sorry, this is mostly governed by output capacitors. Output capacitance, and there are many some more capacitance in the circuit which can determine actually mid frequency and the upper cutoff frequencies. Sorry, upper cutoff frequency may also depend on the other capacitances. We may see if we encounter such questions, then we will solve them and we can see if it depends on this capacitance or not. So for this question, we only need to calculate the lower cutoff frequency, and we have only one capacitor C1 given to us. We need to worry only about that. And it's given that lower cutoff frequency is F cutoff, let's call it as CL, is 10 Hertz. Okay, so now you will draw this equivalent circuit, including this capacitor. Now it's not acting as a short because we need to calculate the value after which, the value for which it will act as a short. And this will be here, this will be G, so this will be actually now VGS, and this will be R2. So this is V out. V out, very simple. V out will be minus GM RD VGS, right? But now this VGS, what is VGS now? You have capacitors and resistors. So this will be R1 parallel R2 multiplied by XC1 divided by R1 parallel R2 plus XC1. Now a capacitance comes into the picture, right? Therefore, gain and this is multiplied. So gain, let's write as we are. So therefore, V out will be minus GMRD multiplied by R1 parallel R2 multiplied by XC. Sorry, I did a mistake here. This is actually simple voltage divider. R1 parallel R2 divided by R1 parallel R2 plus XC1 multiplied by Vn. So therefore, gain is equivalent to minus Gm. One second. So this is R1 parallel R2 divided by XC. Okay, so this is now your gain loading. So now to get a response, so XC1 pole, we will check the pole. So XC1 will be equivalent to, at this pole, it will be equivalent to R1 power R2, and this is given by the inverse of this W, sorry, not W, omega C1. So this will be equivalent to R1 power R2. So we can write it as omega C1, and we know R1 power R2 is 15K, so this will be 1 by 15K. And then I can write C1 as 1 by 15K multiplied by omega, that is 2 pi FCL, and it is given to us as multiply 2 pi multiplied by 10 hertz. Alright, so let's calculate it. Let's calculate it. Okay, so this is 1 by 15 divided by 2 divided by 2.1. This comes nearly around 1 microfarad. Okay, so you know the capacitance unit is in farad, so it's is the option. So this is how you can check the response. We check that this will give you a pole, and that pole will give you a frequency. And you know that after this 10 hertz frequency, the capacitor will act as a short. Okay, now moving on to these questions. Only difference in our analysis now will be that this will be a BJT. So I will draw the equivalent circuit, and you will see that there is not much a difference in the analysis. All right, so okay, so this is a question. Common emitter based amplifier. VCC is 12 volt. Beta in the beta is IC by AB. I hope have read about BJTs. So you can note down these definitions. Beta is IC by AB. VBE on is given as 0.6 volt. VCE saturation is 0.2. And thermal, that is very well known, is 1.6 millivolt. And early voltage is very high. That means early voltage. You must know the definition of early voltage. This is your transistor characteristics. And I draw the stringent similarly like this. This voltage is called as early voltage. More drain bias, sorry, collector bias dependence in your collector current, more will be the sorry, lesser will be. It should be to have a lesser collector voltage dependence in saturation. This VA value should be as high as possible. Magnitude, I'm talking about magnitude. So what if it is like this? Complete saturation. So there is no collector bias dependence in the saturation. You'll see that if you draw a tangent, so it will match it. It will intersect the x-axis at infinity. Okay, so this is a definition of early voltage, and it is given as high. That means there is very less. There is a very high saturation in the device. Okay, and rest of the values are given when we solve. Okay, find the lower cutoff frequency of the amplifier circuit shown in the figure. So we see here that there are multiple capacitances, and from the analysis point of view, how you can get the lower cutoff, that I told you that depends on the input capacitance. So what we will do is, and we will keep C1 and short every other capacitor, like they are not used, okay, while doing the analysis. Okay, so let's draw. And one thing you have to consider in BJT is that there is this. First, we will draw the complete equivalent circuit. Let's call it B. So this will be B. Okay, so this is a complete equivalent circuit or now lower cutoff. So that is depends on C1. So this is important. So it depends on C1. So as I said, we will short the capacitances and keep the C1. So this will basically be like this. Sorry. Since this is short, then this will be something ground. This will be RC. This is how your wait a second. Since it's connected to this. Okay. This is basically so what we need to calculate is we need to find an R equivalent, that's the total resistance, and then use W R equivalent C1 should be greater than 1 or equal to 1, so that will give us a cutoff frequency. So for that we will need to calculate this resistance, let's call it our input. So this is our SR series. So our input will be basically equivalent to R1 parallel to R2, and that is parallel to R5 divided by R1 parallel to R2 plus R5. Just remember the definition for R5. R5 is given by VT by IB. Okay. Therefore, our equivalent is simply Rs plus Rin, and then omega R equivalent C1 is equivalent to 1. Use this equation to get F lower cutoff. So we use the definition as CL, and let me write it as cutoff lower is equivalent to 2 pi R equivalent C. So now what we need to calculate is R equivalent. So for that I need R1, R2 is given. I will just need IB, IB for IB. We need IC because then we can write since beta is given. Since beta is given, beta is IC by IB, and then IB will be equivalent to IC by beta. So we can find IC. So we had to do a DC analysis, right? Okay, so let's DC analysis. Let me just draw the circuit. So this is R1, R2. Just remember that for DC capacitor sectors. Okay, so this is RC here, and this is VCC equivalent to relevant. Okay, what we will do is we'll follow a KVL on this region to this region. Alright, this is emitter, this is collector. So if I do a KVL here, so this will be 12 minus voltage drop across this one minus this is a VBE that is KL minus a current of IE flows here 0, and we can write VR1 as R1 divided by R1 plus R2 multiplied by 12. That is, I have just written down the values here. It is 8.4K divided by 8.4K plus 3.6K multiplied by 12 is equivalent to 8.4 divided by 10. So this is 8.4 volt. Okay, so therefore we can have 12 minus 8.4 and VB on is given as 0.6, and this is equivalent to IE multiplied by RE. RE is 2K ohm. So IE comes out to be equivalent to 1.5 milliampere. Alright, now we know from BJT analysis IC plus IB is equivalent to IE. We can assume IC is equal to beta times IB. IC is 200 times IB. Therefore, IB is IC by 200. We can assume it IC is nearly equivalent to IE. Therefore, it will be 1.5 milli divided by 200. That comes out to be 0.00 7 million here. So therefore, R pi, we just needed to calculate R pi, that is dP by IB is equivalent to actually now 26 millivolts divided by 0.007775 millivolts. So this will be 3.46 kilo ohms. So this is R pi. Now R1 further R2 is 8.4K multiplied by 3.6K divided by 12K, and that is equal to 2.58K. And thus R1 parallel R2 parallel R5 is equivalent to 2.52K multiplied by 2.462 divided by 3.46K. It comes out to be 1.45K. Therefore, R in is equivalent to 1.45K, and therefore R equivalent is RS plus R in. This means R equivalent is RS is given right 81 plus 1.45K, that is nearly 1.45K. Therefore, F1 is 1 by 2 pi R equivalent into C1, that is 10 micro. This is 3. Transforming will get 2 pi. And this comes out to be alignments. So I hope this is clear. So here about the answer here is this PPA. So this is how you solve these type of questions. Similarly, if we had to calculate alpha, let's see if next questions focus on yes. So now we have upper cutoff frequency. So let's assume CL determines upper cutoff frequency. Alright. Since we know the output capacitance says a determining factor. So I have basically equivalent circuit as like this. This will be 0 since this is 0, so this will be 0. There won't be any current here, so this is basically RC. And this is capacitor CN. So you see a resistance are equivalent is simply RC. So what I need to write in the upper will be simply equivalent to 1 divided by 2 pi RC into CL. So that is equivalent to 2 pi into this is 4K multiplied by 100 equal. We solve this and we'll get to 402 volts. So the option B. So this is how you can calculate. You just need to calculate the resistance, equivalent resistance across that capacitor, and use this relation. Okay. Now we have given omega. Omega is 200 radian per second. Okay. So let's assume this is that means 2 pi f will be 200 k multiplied by sorry this this will be equivalent to 200k. So F will be 200k by 2 pi. That comes out to be that will be 100 divided by 204. So this is 31.84k. So this is actually above lower cutoff and below upper cutoff. So it is actually in the mid frequency range, right? Okay, so equivalent circuit will be like this. Let's assume that the capacitors are short. All right. So this is V in, this is RS. So VBE is RN divided by RN plus RS into V in, right? And now the output can just directly write it as the output by V input is equivalent to GM. This is RC parallel X here, right? This is not actually V in, this is VS. One second. Okay, we use V in here. This is VB, so it is actually it was actually V in. So V in. This is equivalent to this GMRC parallel XC. So in terms of frequency or S term, we can write it as GMRC divided by 1 plus RC GMRC CL S. Okay, so taking the magnitude, you will get GMRC divided by 1 plus RL CL S square. Okay, now what is GM? GM for BJT is simply IC by VT. It is noted down as well. IC is 1.5 milliampere, while VT is 26 millivolts, so it comes out to be 0.05. So to substituting it level relation, you will get V output, the V input is equivalent to 0. 5 multiplied by RC is 4K, times for 3 divided by 1 plus 4 times for 3 multiplied by the capacitance values. Okay, and it comes out to be 119.4. Okay, Okay, before we go there, see the things. Okay, so let us draw the circuit. This is a series RCM. Okay, so let's start. What is this? Let's call it as R2 equivalent. R2 equivalent is R2 by C2S divided by R2 plus 1 by C2S. You should know that capacitor in S domain is represented by 1 by Cs, right? So this is R2 divided by 1 plus R2 C2S. Okay. Now the output is equivalent to R2 equivalent divided by R2 equivalent plus R1 plus 1 by C1. And it is just follow the mathematical steps. It's very simple. For the simplification, we need to relation like this. solve this by yourself. Okay, in this step, we'll assume that this term is very less than the other terms. Actually, simplify our analysis. What we do like this, yeah, output plus input is. So you see that we had two capacitors. So now we see that we have two volts here given by V1 as 1 by R1 plus R2. Pole is nothing but a frequency V1S, and another one is V2, 1 divided by R1, R2 divided by R1 plus R2, V2S. Okay, so in this way you can write any circuit. Just find the transfer function and write the denominator in this form, and you can get the whole. Similarly, in the numerator as well, that those are called as zeros. So every transfer function has a zero and a whole. By using your transfer function, you can always find them. Okay. So next, before we go to another sections, we need to study an important term that is called as Miller's theorem. Okay, we'll just go through its derivation. One second. Okay, so this is your circuit. Okay, now you see that there is an impedance Z that is connected from input port to output port. What Mellotron does is Mellotron decouples the impedance, okay, and write it into parts Z1 and Z2. Z1 to the input and Z2 to the output. Now let's see what are the values for. Let's say this is a network and this is V1, this is V2, and this is the impedance connected from input port to output port. Let's say this is the input resistance of RL, and this is I, this is I1, this is I2, and this is the total Z in. We will calculate this Z in. Okay, let's see. So at input, I is equivalent to I1 plus I2. Okay, so I can write it as V1 by Z in is equal to I1. That is simply V1 by R in is I2. That is V1 minus V2 by Z, right? So now V, what is V2? It's a gain times V1. Okay, so I can write V1 by Z in is equivalent to V1 by R in plus V1 like this, right? Cancel V1. So this is basically 1 by Z in is equivalent to 1 by R in plus 1 divided by Z divided by 1 minus A. So this is actually the impedance looking at the input. Similarly, at output, at output, see that V2 minus V1 by Z is equivalent to V2 by Z out. Okay, so this will be A times 1, A times, sorry, A2 is, V2 is A times V1. So this will be basically V2 1 minus 1 by A by Z is equal to V2 by Z out. V2 and V2 cancel. So this is basically Z out is equivalent to Z divided by 1 minus 1 by 3. Now look here, so I can write Z in as 1 by R in plus 1 by Z Miller input, and this is Z Miller output. Okay. So you see, Z Miller input is simply Z divided by 1 minus A. So now you decouple this is equivalent to Z Miller input Z Miller output. Okay, and know the values. Okay, now what if this Z was a capacitance? Let's call it a CF. So then, see Miller input, try to solve this. That will be equivalent to CF times 1 minus E and CMF is equal to C minus right, 1 by A. So this is basically, you just have to substitute in place of wizard, you have to substitute 1 by CF and you will get the capacitance contributions. Okay, so what we have studied till now, we check the frequency response. Okay, let's see. Okay, so in these questions, you just saw that we ignored these values. C pi in this as well, in this as well. Hmm. So there was no need of Miller. Um, let's see. Okay, now the question is find the effective input capacitance looking into the base of the transistor for the amplifier circuit shown in figure 5.1. Okay, here is the circuit. What we need to do is we need to find the effective input capacitance. Okay, consider the effect of parasitic capacitance. C pi and C mu is given as like this. So now your equivalent circuit. C in will be C pi plus C mu is actually this capacitance. We have to do. And C in will be C pi is this capacitance. Now, one second, it will be a confusion. It will create a confusion. So let me just draw it with a different color. Basically, first there was a capacitance of C mu from this node to this node, and capacitance of C pi from this node to this node. Okay, now we calculate C in, that is the effective capacitance. That will be C pi plus C mu times 1 minus A. And what is A? A is simply minus GM RC. We had calculated the GM in the previous part, so that was equivalent to 0.05 and RC is 4K. So this comes out to be minus 240. So therefore, C in is simply C pi plus C mu 0.01 And this is C pi is given as 12 picofarad, right? And plus this is 6 pico multiplied by 2. 1 second. This is 51. And this comes out to be CE 1458 picofarad. 1458. It's like the closest option, so this one is the closest option. I may have done some mistake in the calculation, we can check. Alright, so what next? See here, we have to find upper cutoff, right? Initially, it was simply CL. Now we have to construct of upper cutoff as 2 pi R equivalent, C equivalent, right? Now, because due to Miller capacitance, there will be the capacitance at output as well, right? The total C out will be CL plus okay, that was CL 100 pico. CL is 100 pico plus 6 pico. 1 minus 201. Sorry, this I need to. Okay, let's see. Hmm. Okay, CL, assume the CL is the total capacitance because there are two capacitors. Assume that as equal or series with what is another capacitance? Let's first check. Just ignore that capacitance. C2. C2 is 10 microfarad, right? So CL is 100 pico in series with 10 microfarad. So it is actually nearly equivalent to CL only. And then you add the capacitance due to Miller capacitance. So actually, what was the definition? 1 minus 1 by A. Correct. So you can just calculate this total capacitance, C out, and then you, your cutoff, upper cutoff will be 1 by 2 pi. R equivalent is simply 4 kilo multiplied by this is nearly 106 pico. Okay, solve this and get the answer. So let's go to what we did in this session. First, it was a very basic question. Calculated simply again. So that must have been a sort of a repetition for you guys. I think we discussed enough in this session. Go through the video. If you find anything to discuss in the last session, we have last session on the coming Tuesday, so we can discuss on that on Tuesday. So here we discuss simple things first, and I have shown you this method of calculating the distances. Then okay, so hmm, okay, so we will see about this mid frequency. We will see in the next session. We will see some questions related to the other capacitors that may determine your upper cutoff frequency. All right. So this is how you should be. We should be able to now. You should be able to now derive the and gain using the capacitors as well. Then that's called as a transfer function. And then from that transfer function, just substitute. Use this equivalency to find the poles. So this will give you. And just a reminder that input frequency on most of the times, I guess mostly, determines our input cutoff frequency. This is the relation to use. And then we had this question, set of five questions, in which first we didn't need to use these parasitic elements. So the analysis was very simple, equivalent circuit, and for a particular capacitor, use that capacitor in the circuit and short all the capacitors, and that will give you the answer. And this is okay. So this question gave you a slight bit of introduction to the BGT. Try to get these relations like GM, R pi from your end as well. Okay, so basic BGT formulation like IC plus IB is IC is beta times IB, and similarly alpha. You can use those. Those are very basic to BJT. Okay, then the most important, okay, this is first the frequency response, just to check how you can calculate the poles in the circuit. Okay, go through it. And then most important thing that we discussed in this session was actually the Miller's term. It's a very handy tool to use this Miller's term, in which we decouple if there is a connected input, if there is a connected element between the input and output, that can be decoupled using this term. And these are the two steps. And this is how you transform your circuit while using this. Yeah. Okay, this we use, this is a basic BJT equivalent circuit where CMU is connected between base and base and one second, base and collector, and C pi is between base and emitter. To decouple, we use a Miller's term, and already there is C pi. C pi will then be in parallel with C mu times 1 minus E. That comes from the Miller's term. Okay, again, simple, minus GMRC. And GM, for a BGT is IC, VT by IC by VT. Okay, so this is it. And at last, we calculated the C output, upper cutoff frequency, depending on the C output. So just a second. The CL let me call it CL dash. CL dash is actually CL parallel C2. Sorry, not parallel. CL in series C2. So CL dash is equivalent to CL C2 divided by CL plus C2. Solve this, you will get CL dash as nearly equivalent to CL. That's why I directly use 100 picofarad here. So this sums up today's session. In the next section, and that was the last session, we'll go again through this frequency response and see if you join, and we'll see if there are doubts related to this course, so we can discuss that. So let me end the session now. Hope to see you next week.